So let me say a few words, ladies and gentlemen. Good day to all of you, wherever you are. We are really delighted to celebrate with the UAE Space Agency the spectacular success of the launch 2 days ago of the Mars mission HOPE. Our warmest congratulations to the Space Agency and to the Mohammed bin Rashid Space Center, all the UAE scientists and engineers who worked on the project, and in fact to the entire citizenry of this country. There's nothing more inspirational for celebrating the 50th anniversary of this country. And the name HOPE is so appropriate, especially considering the dire situation in which we find ourselves today. I feel energized by the excitement that this nation as a whole has been experiencing in the last few days about the launch, especially the young people. So first of all, warm congratulations to all of you. My name is Srinivasan. I'm the principal investigator of the Center for Space Science at NYU Abu Dhabi. We created this center with the dual purpose of promoting space science within the university and also providing intellectual support for the UAE Space Agency and MBRSC. Indeed, this event is jointly organized with the UAE Space Agency. Today's program features 4 extraordinary speakers who are experts on different aspects of Mars. I will let Dimitra introduce them to you properly when the time comes. But I simply want to express my gratitude to them all for agreeing to speak at this event. Dimitra will also say a few words about our center and its work. Before the experts speak, we have the great pleasure of hearing from 2 distinguished speakers, Mariët Westermann and Fahad Mheiri. Professor Westermann is NYU Abu Dhabi's Vice Chancellor. She is a great supporter of our center and its collaboration with the space efforts in the country, as her presence here indicates, even though her attention is constantly being demanded elsewhere during these difficult times. Thank you, Mariët. She will be followed by Dr. Fahad Al-Mheiri, the Executive Director of the Space Sector of the UAE Space Agency. As you just heard, probably, he is an extremely busy person now, especially after this successful launch. And so thank you, sir, for being here. Before coming to the Space Agency, he was the Director of the Business Development at the Emirates Defense Industries Company. Thank you again. Before leaving the floor, I wish to thank the many people who have made the event possible, particularly Dimitra Atri and Tamara Withers at our center, and to the various NYU Abu Dhabi staff. At the UAE Space Agency, Dr. Fatima Aldaruz, the space sciences expert, and its Director General, Dr. Mohammed Al-Ababi, who also serves on our center's advisory board. To all the members of our board who have tuned in, including its chairman, Dr. John Leibacher, I send my greetings and thanks. And I thank again the speakers and congratulations to the UAE space efforts. And now, Mariët, please take it away.
Thank you so much, Srini, and good morning, good afternoon, good night, wherever you may be in the world. Certainly, NYU Abu Dhabi and its Center for Space Science are delighted and proud to co-host this mini-symposium on the future of Mars research with the UAE Space Agency. It is a special pleasure for me to be with you in this truly historic week for space exploration, for science, and for technology in the UAE, our country. I want to congratulate the country on the successful launch of the Al-Amal mission to Mars just yesterday, and especially co-panelists here, Dr. Fahad and Dr. Fatima. It's really great to be with you. And we also wish warmest congratulations to His Excellency Mohammed Al-Ababi, Director General of the UAE Space Agency, a great friend of our center, as is Her Excellency Sarah Al-Amiri, the Minister of State for Advanced Sciences and Deputy Project Manager of the Mars mission. Really, congratulations to all of you. It was very moving. I witnessed the takeoff. It was very moving to see it, and especially to think about how soon that was after Hessa Al-Mansouri, the UAE's first astronaut, returned to Earth safely last fall. That was a very signature moment for space science and astronautics in the UAE. And I want to say that this, although I am an art historian, I'm indeed very far from an expert. This is more than a general story of fascination and pride in the country for me. I've been an amateur astronomer since I was a young teenager, actually since I was about 10 years old. And I remember one of the highlights of my teenage years in developing my interest in the field was the Viking mission of 1975-76, the one I really followed closely because as this signature moment in Mars research. And it is just incredibly exciting to me, years later, and still an amateur astronomer, to see the UAE take the next step in what will be crucial Mars research. So I'll try to, after the intro speeches, I will actually want to hear a little bit from all of the experts. One of the things for me as an educator and Vice Chancellor of NYU Abu Dhabi is it's exciting to see such a young team of scientists and engineers assembled only 6 years ago. Mabruk, you know, even before the birth of the space agency, built the probe from the ground up in collaboration with so many around the world. And since I am among scientists here, I can say in this community that, like the probe, NYU Abu Dhabi is itself a very special and still very young experiment. We've been operating for 10 years, as you know, as an educational institution. And to date, I think it's been a highly successful one, although certainly we didn't know how it would turn out. The mission of NYU Abu Dhabi is to be a world-class university in and of Abu Dhabi and the UAE, in and of New York University as a global university, and certainly a university meant to be in and of the world and for a better world in particular. So like the Center for Space Science, or that's such an important part of us, we seek to contribute to knowledge development in all of these communities, in the UAE, in science and engineering, and in the world community at large. And we do it through our undergraduate education, through our beginning graduate programs, PhD programs, and through advanced research. And alongside that, as Srini has already said, we also want to contribute vigorous public programming and knowledge development so that the intellectual and artistic culture of the UAE is enriched by everything we do. And we do this in collaboration. And I think the Center for Space Science, which is one of our younger and already very successful centers, is really built on that model of participation and collaboration. I really think our partnership with the Space Agency and the Mohammed bin Rashid Space Center is just a shining example of how we want to collaborate with the local intellectual and scientific community and agencies. I also want to say that the Amal probe, the Mars probe, built here with local and international scientists and engineers, launched from Japan, involving so many around the world, is a great example of international solidarity that we need today, international collaboration, more than ever. And what I think is so impressive in this year of great challenges for the world, especially the health challenge, but along with that, economic challenges, it would have been understandable if people had said, oh, we take a pause on this, we can do this later, we wait a little bit. But the UAE has said very declaratively by launching the probe this week, we can do both at the same time. We cannot put our lives and our advancement on hold. We have to keep working in all these different ways together. And I think that that is very exciting. I think that it is inspiring, in fact. And it is clear from when you look at the news reports around the world, people have been following this, that the probe is already achieving one of its goals, which was to inspire more and develop more scientists and engineers here in the UAE and around the world. And this is exactly what NYU Abu Dhabi's mission is. We ourselves want to develop and support young scholars, scientists, engineers, entrepreneurs, artists, and creatives from the UAE. Almost 20% of our students is from the UAE, but also from 120 other countries around the world. And all these students and our professors and researchers from many, many countries come together to learn science and engineering, to develop new ideas and invent new creations in all of these different disciplines, including the sciences and engineering. In closing, I want to say one special point of pride for me, and I have sometimes mentioned this, I think, to Her Excellency Sarah. A special point of happiness and pride for NYU Abu Dhabi is that, in fact, more than 50% of our STEM majors, our science and engineering majors, are young women. And given that the UAE also has invested so much in the development of all scientists, but also women scientists and engineers, I think that's a very significant point of convergence and synergy between our missions. So I am really looking forward to following the very important atmospheric science that will be advanced through the probe when it arrives in Mars early next year. It will be so important for our understanding of the possibilities of life beyond Earth, but also I think the future of our own planet and humanity's role as one of the planet's stewards. So thank you very much for giving me this opportunity to say a few words and to be with you. I wish you a very, very engaging symposium.
Thank you, Mariët. It's very kind of you to take the time and talk to us today. Dr. Fahad, could you please say a few words? When I was watching the launch, it was interesting to see the countdown in Arabic, which I had never seen before, of course, and also commentary in Japanese interspersed together. So it was a very interesting experience, even outside the excitement of the launch itself. So, Dr. Fahad.
Thank you very much. And thank you to NYU and the team at the agency and everybody that's here to make this symposium, inshallah, a very eventful and very educational session. And thank you really also for allowing us to shift it. I think initially this was supposed to take place on the same day as the launch event. And, you can imagine I was probably pulled 20 ways that day. So thank you very much for allowing for this shift. I'm much more relaxed today, a lot less worries. And so, in a lot better situation to be able to open up and talk. Of course, alhamdulillah, with the wonderful, event and the successful launch that took place, that was just something phenomenal. Unfortunately, I was stuck in a studio. I couldn't see anything. I didn't know what was happening, but I'm really happy and I'm so proud of the EMM team for having achieved this. And one of the main things I felt, being there at that studio is the immense energy that was coming through the people whenever we fed live back into Japan, or whether when we went back to MBRSC or spoke to anybody. We had speakers from the UK, we had speakers from the US, we had speakers from Canada, and it was phenomenal really to see their reactions after the launch and how happy they were. This really shows, it's almost as if this is the first time the Arabs have launched anything into space, We have a program that's already been running for many years, but the aspect of Mars, the science behind it, the whole space exploration aspect was something completely different, and it took this to another level completely. So just really, I'm so proud of the team, so proud of everything. I mean, I've only been at the Space Center, at the Space Agency here, for 5 months now. At launch, I was hitting 5 months on the day. It's been 5 months and a couple of days now. So it was really, an immense amount of pride for me to see that and be part of it. And then for me to be at the studio and represent the UAE Space Agency was fantastic. So, for me, I would really like to thank the NYU and the Center for Space Science to arrange this. I am really interested to learn things here today. One of the things preparing myself, I would say, for what's to come was reading really about, the other missions that we're going to be talking about today, Perseverance. I read a lot about Curiosity, about Insight, about MAVEN, and also really intrigued about what the Chinese are about to do as well. They're going to be setting quite a few firsts with, the first debut for their rockets, and then actually having all three, an orbiter, a lander, and a rover, all going to Mars in one mission. So if this window goes well and the US launch Perseverance with ingenuity, there is going to be so much new science that is going to be coming out once everybody arrives, inshallah, around February to coincide with the UAE 50th Jubilee. And I'm sure the space science sector of the world is really keen and excited, just as much as we are. I mean, I can see, in the chats, we have people from all over the country joining us here today. And that shows you really the immense interest in this project and in this program. I would just really also, just touch on what was mentioned, and the EMM science team do consist of 80% women, which is phenomenal. And throughout the program, it was 34%. The average age, 27 years old, the average age. And that was quite a funny thing when we were speaking to an expert over in the US. And he was saying, I'm, mid-career and I'm already, in my late 40s and I'm still considered to be a young person in this field. So, what this does for the generation and what this opportunity is for Arabs is tremendous. I'm sure most of you have heard as well about the new Arab Space Pioneer Program. This was also launched by His Highness Sheikh Mohammed bin Rashid. Seeing how much this project touched and affected, STEM education, how much it inspired the world, inspired UAE nationals. And, through his generosity, he has expanded this now to the whole Arab world, which means we have received actually 37,000 applications to date that we are currently filtering through and going through, and will be separating in different tracks, giving Arabs all over the world the opportunity to come here to the UAE and also be part of what the country is giving the UAE nationals in this country. So giving opportunities to all Arabs around the world to be part of the whole science aspect. When we work together in such collaboration and partnership, that's really the only time we will be able to succeed. We're not going to reinvent the wheel. The international partnerships and cooperation is tremendously important for us. We have over 28 countries that we have MOUs with already and that we're working together. We probably have more than 100 different NDAs with different companies that we're looking and working towards. One of the main things that really makes us proud about the EMM, we didn't just go out and buy a satellite. We didn't go to a big company and say, oh, hey, this is what we want. We want a satellite that can do this. We can put our name on it and say it was ours and send it up, and we wanted that. No. His Highness was very clear about that. This was going to be a project to be built by UAE nationals, which means we did it differently. We didn't go to the big companies. We went to knowledge partners. We had 3 different knowledge partners from the US who we worked with. They were not professionals. These guys are professors, teachers, academia, and other students that were there. And together, because they've already had experience in doing such projects, we worked together with them. So UAE nationals had hands-on experience in making all of this happen. And this is where, the fantastic thing about all of this project is, a lot of people are concerned that, yeah, it was built in the US. Yes, because the infrastructure doesn't really exist for us here. The knowledge and expertise, the ability to, reach out to a neighbor here doesn't exist yet. But now we have over 250 UAE nationals that have been through that process. And so it makes me so proud to think that we could do this again as Arabs here, possibly in the country. So I can talk a lot more about this and how proud I am about the whole event, but I'm really here to learn as well from you guys. I would love to know what's happening and what's next. And we really look forward to getting the data and be able to take the next step forward and really focusing on the data science. Thank you very much for being with us here today. And I really look forward to this session.
Thank you so much for your very inspiring words. I'm sure the audience are inspired as well. I know how many young people in the country are excited about science, space science now, and I think this is an extraordinary event. So Dimitra, why don't you take over the rest of the program?
Right, thank you, Srini, and thank you to Professor Westermann, to Engineer Fahad for coming here and supporting this symposium and our Mars research program. So as you all know, that July 20th has been known in the space community as a historic day, because in 1969, Neil Armstrong and Buzz Aldrin set foot on the moon on the same day. But because of the successful launch of the HOPE mission, July 20th has a new meaning now in this region. And so, that has been possible because of the hard work of the entire EMM team. And I'm proud to introduce our first speaker, Hessa Matroushi from MBRSC, who has been extremely busy over the past several weeks, but she took time off from her busy schedule to be here. She is a science data analysis and management lead. Since 2015, she has been a part of the mission from the very get-go. And congratulations, Hessa, and start whenever you're ready.
Thank you so much, Dimitra, for the introduction. I'm very pleased to be part of this symposium and to share the story of the Emirates Mars mission. Let me share the screen and my presentation. All right, can everyone see my slides?
Yes, we can.
Yeah.
All right, so this is an overview presentation about the Emirates Mars mission. I'm Hessa Matroushi, Emirates Science Data Management and Analysis Lead, and I'm part of the core science team of the mission. I've been part of the mission since 2015, a long time ago, and I can't believe that we're right now, like sitting at this time with the mission has launched. At that time, I remember like thinking about 2020 a long time ago. We still have time, but now is the time. And we're looking forward for the probe to reach Mars and to get our hands on the data so we can have this amazing science going on. I would like to start my presentation by talking about the story of the Emirates Mars mission. So it started by the announcement that was done by the UAE government in 2014. So the announcement was clearly made that we have 4 strategic objectives when it comes to the Emirates Mars mission. The first one is about completing Mars orbit insertion by the UAE's 50th anniversary in 2021. So that automatically directly put us in a launch year in 2020, because we can only launch to Mars once every 2 years. So that cannot be done in 2021, only in 2020. And that's why we planned our launch to be in this summer, 2020. So we are able to reach Mars before December 2021, where the UAE will complete its 50th years. The second objective is to contribute to the development of the science and technology sector in the United Arab Emirates. So we would like to utilize this mission to radiate the development in the science and technology sector. So we want to reach out to the community out there and develop them alongside of us, the team of the mission. The third objective is to develop UAE scientific capabilities. So the space sector has been established in UAE a long time ago. Specifically talking about the center that I'm coming from, Hamad Ibrahim Space Center, it was established in 2006. And we had a lot of, we had a space program that was focused on developing the UAE engineering capabilities. And that was very much set with having DubaiSat 1, DubaiSat 2, and even KhalifaSat, which was 100% built by UAE nationals. But the scientific capabilities needed more developments. So we wanted to utilize this mission to develop specifically the science aspects when it comes to space science as well. And the fourth objective was increasing UAE's contribution to the scientific community. We wanted to add value when it comes to the international scientific community, to bring new knowledge, to fill in some gaps that already exist when it comes to Mars science. So that automatically translates into a unique mission that we need to come up with when it comes to the science, and even when it comes to managing the project itself, because by announcing this in 2014 and putting a deadline of launch in 2020, we only had 6 years to do the development of the whole mission, doing the design, the testing, the development, and the assembly. And that is a very much shorter time compared to the other missions that we have gone to Mars. So we had a lot of challenges in front of us, but we were very excited to tackle them because it is for the benefit of everyone. Within the name of the mission, hope, we want to use this mission to radiate hope, to develop the country and move forward and be an effective contributor to the international science community. Within the mission, we wanted to focus on the atmosphere of Mars. So if we look at the graph that we have, or the picture that we have at the right, this is the Martian atmosphere. We can see that we have different layers in the atmosphere in there. We have the lower atmosphere, and then the middle atmosphere, and then the upper atmosphere that consists from the thermosphere and the exosphere. So the motivating science question that motivated the objectives of the missions are three. The first one says, how does the Martian lower atmosphere respond globally, diurnally, and seasonally to solar forcing? So we want to characterize the lower atmosphere, and the lower
We froze somehow.
Atmosphere extends from the surface up to 50 kilometers, and there are dynamics. Are you able to hear me?
Yeah, you were frozen for a while, but now you were okay. Yeah.
All right. So I was saying that the first questions, through the first question, we would like to characterize the Martian lower atmosphere that extends to an altitude of 50 kilometers, and we would like to study the key constituents in there. The second question is about relating the conditions in the lower atmosphere with their impact and their effect of the escape rate that happens in the upper atmosphere. So we know from the studies that have been done in Mars that a lot of gases are escaping the Martian atmosphere, and it's a very thin comparing to 4 billion years ago where the Martian atmosphere was very thick. So we would like to understand how these conditions are impacting the escape, especially for the hydrogen and oxygens, the building blocks of water. The third scientific question is about characterizing the exosphere. So we would like to understand how it behaves temporally and even spatially. So we know that through the exosphere, gases are escaping Mars, especially hydrogen and oxygen, and we would like to characterize how this layer behaves throughout the seasons and even in a daily manner. So these three scientific questions translated to one-to-one scientific objectives that we have for the mission. And these scientific objectives, we needed measurements to be done. So these where we have the scientific investigations, we do have 4 of them. And we can go over one, explaining them one by one. So at first, we have the first objective, as I mentioned, is about studying the lower atmosphere. So we have 2 investigations to fulfill that. At first, investigation 1 focuses on determining the 3D thermal state of the lower atmosphere. So we'd like to understand the temperature behavior and the thermal state of Mars. The second investigation focuses on studying the key constituent in the lower atmosphere. So we'd like to understand their diurnal distribution, the geographic distribution of these constituents over the day and over the year. And then we do have an objective 3, as I mentioned, about studying the exosphere of Mars. So in here we have investigation number 4, which is about having a 3D structure and variability of the key species in the exosphere. And those key species that we will look into are the hydrogen and the oxygen. And then objective number 2, which is about correlating the lower atmosphere and upper atmosphere. So we do need all 3 investigations that I just mentioned, in addition to studying the thermosphere layer. So the thermosphere layer is the lower boundary of the upper atmosphere. And this layer is very interesting because it is impacted by the dynamics of the lower atmosphere, and it's impacted even by the solar activities that are penetrated from the upper atmosphere. So it's a very good layer in order to know the correlations and the impact of the lower atmosphere at the upper atmosphere. And this is how we got our scientific objectives. So one can ask, what is unique about the Emirates Mars mission? So, and some ask, like, haven't we studied the Martian atmosphere before? Yes, we did, but we are here to fulfill a scientific gap. After meeting with a lot of international scientists in the field, we understood that there is a limitation when it comes to the data of the Martian atmosphere. We either have missions that sample the geographic area at one local time, thus we can't know like in details what happens throughout the day and how the atmospheric processes changes. And then if we did so and we study throughout the day, we are limited by a specific geographic location. So we don't have a global coverage when it comes to that. So Emirates Mars mission is the only mission now that will have a combination of a global geographic coverage and a local time coverage. And we will do that diurnally, and we'll study it sub-seasonally for one whole Martian year. And to enable this kind of science, we have a special orbit that no one had flew to before. So our orbit dimension is 43,000 kilometers by 20,000 kilometers. It have an inclination of 25 degrees. As you can see, like, it's a very wide orbit compared to all the other orbits that other missions had flew to when they studied Mars. But this is what enables our science. This is what allow us to have this global coverage and measurements of observations of Mars, and it can allow us to study the upper atmosphere up to 30,000 kilometers as well, enable us to characterize the escape rate of hydrogen and oxygen. And the spacecraft can take 58 hours just to go for the whole orbit, and we'll be taking multiple observations during that. So the development of the mission started in 2014, and we went into developing the concept, structural design, assembly and integration, until we reached today to the point where we launched the whole probe. And now we're looking into our next milestone, which is Mars orbit insertion in 2021. After that, we will begin our scientific phase that will last for one Martian year to enable us to study the atmosphere in its all seasons. And one Martian year equates to 2 Earth years. And then after the scientific phase ends, the probe is able to operate for an additional 2 Earth years. So we can have an extended scientific operation after that. I would like just to put a small video about the launch. So you saw just now the project manager of the Emirates Mars mission, Imran Sharaf, counting down in Arabic for the probe to be launched. And this was the first Arabic countdown, which was very exciting. So we launched from Japan, from Tanegashima, July 20. The launch speed was 34,000 kilometers per hour, which we are anticipating a cruising distance around 500 million kilometers. Our cruising phase will last for around 7 months, reaching Mars in February 2021. I do have another short video as well to walk you through the phases of the probe. So we had our first UAE contact around an hour after the probe was launched, and it was very successful. We made sure that the probe is functioning well. The thermal state is all green, and it's now in its cruise phase going to Mars. So you can see the blue circle in the video. This is Earth, and then the yellow circle, this is Mars. And the green line shows the probe approaching Mars in order to begin the Mars orbit insertion as a next phase. You can see now it's approaching, and now we can start with the Mars orbit insertion phase. Mars orbit insertion is a critical phase in which the spacecraft needs to be captured by Mars gravity so it can go into orbit. You can see the green line. This is where the spacecraft is approaching. And this phase will last for around 30 minutes, and it's very critical because it needs to be automated. As you know, the signal to reach from the probe to Earth can take from 13 to 26 minutes. So there's nothing that we can do during this phase, and it's all programmed so it can tackle this kind of challenges. You can see the thrusters, they will be braking, so we can reduce the speed of the probe so it can be inserted into the Mars orbit. You can see even two views for this insertion. And after the Mars orbit insertion is successful, it will go into a capture orbit, this is the next phase. We're not going directly to the science phase. At first, we're going to a capture orbit, which is its dimension around 500 kilometers by 40,000 kilometers, in which we will do instrument calibration. We'll make sure that our probe and instruments are behaving as necessarily before we commence our science phase afterwards. So you can see the dimension of the capture orbit, and we are planning to stay there for around 2 months to make sure that everything is working well and as intended. And then we will transition to the science phase and to the science orbit, which is a wider orbit compared to the capture orbit, which you can see in orange right now. And we will stay there for 1 Martian year, as I mentioned. And I can speed up this video to show you how the coverage when it comes to Mars, as we're getting data, so we can sample the whole globe at every time. This mission would have not been successful without its international collaboration. Although we have a space program here at Mohammed Barash Space Center, what we've done is Earth observation satellites, but we haven't sent a probe to explore another planet. So this is a first for the UAE and even for the Arab region. So we wanted to establish a knowledge transfer program where we have 3 partners university. We have LASP from University of Colorado Boulder, we have SSL as part of University of California, Berkeley, and we have Arizona State University as our key partners in this mission, in which we work together, as you can see in these images, as part of our regular meetings that we have face-to-face. But the science team is more diverse. It has members from all these institutions, as well as the space science, and we have from L&D as well. And we have even individuals that are associated with other entities as part of the team. And we have our partners for navigation, Kintex, and we have MHI, of course, as part of our launch partner. We have 3 scientific instruments on board of the whole probe. We have Emirates Mars Infrared Spectrometer, we call it EMMS. This is the joint development by ASU and MBRSC. And then the second one is Emirates Exploration Imager, EXI. This is a joint development between LASP and MBRSC. And then the third one is Emirates Mars Ultraviolet Spectrometer, EMUS. This is a joint collaboration between LASP as well and MBRSC. And you can see the schematics up there and the real images of the instruments down there, which looks very beautiful. I will show you the key characteristics of each instrument and what kind of data we will get from them. So we will start first with the EMMS instrument. EMMS is a Fourier transform spectrometer instrument. It has a spectral range between 6 to 40 micrometers, and the spatial resolution will be less than 300 kilometers depending on the distance we are, because we have an elliptical orbit, so we are at a different distance from Mars at each point. It has a 6 millirad instantaneous field of view, and we will be able to absorb half of Mars within half of hour of observing. So we can get 20 observations per orbit. EMMS will focus on studying the lower atmosphere of Mars. It will give us information about atmospheric temperature to understand its thermal state. It will give us information about the surface temperature, so as it's the lower boundary of the atmosphere, as well as information about its key constituents like water vapor, ice optical depth, and even dust optical depth. Complementing EMMS and its study in the lower atmosphere, we have EXI. EXI is an imager, 12 megapixel imager. It will give us a dynamic range of 12 bits. And if we look at the ground resolution, We have 4.9 kilometers per pixel at apoapsis and 2.3 kilometers at periapsis, so very high resolution imager. EXI has 6 spectral bands. 3 of them are UV bands, and 3 of them are red, green, and blue, which will give us beautiful images of Mars. And through these visible images, we will be able as well to observe the surface and to look at the changes that happens at the polar cap. The science targets of EXI are water ice, ozone, and the colorful images will give us information about the surface as well and the changes that happens. We can as well observe the dust storms during the, while watching and analyzing these images. The third instrument is Emirates Mars Ultraviolet Spectrometer, EMUS. EMUS is the only instrument that will focus on the upper atmosphere of Mars, giving us information of the thermosphere and the exosphere. It has a spectral range of 100 to 170 nanometer with 3 spectral resolutions. So we have 3 slits on board of this instrument, 1.3, 1.8, and 5 nanometers, with a similar spatial resolution like EMIRS, less than 300 kilometers. The science targets of EMUS: in the thermosphere, it will be carbon monoxide and oxygen, and in the exosphere, it will be oxygen and hydrogen. And this is how these 3 instruments will be complementing each other in terms of data and science. Here is our spacecraft with an open solar panel. So the dimension of the spacecraft is 3 meters by around 8 meters with the solar panels open, and it has a wet mass of 1,500 kilograms. A question that we get a lot is about the data that we will get from the whole probe and the 3 scientific instruments. So we will have a website called EMM Science Data Center that we will release all the data in there to be accessed by everyone. So it will only require an account registration, and everyone can register in this website, and through which you can download the data that you want by selecting which instrument and data range and data levels that you would like and interested to download. And you will get, even through the registration of account, notification of new releases that will come from the data. So we're starting our science phase around May 2021. And the first data release in the website will be around September 2021, so 4 months after we start the science phase. And then we will have frequent data releases every 3 months afterwards. The website will provide data access, which will provide quick looks and even visualization tools to ease the selection of the data. And it will have a calibrated data from level 2 and level 3 accessible to all public. As I mentioned before, we had a lot of objectives. Some of them were about the uniqueness and the science of the mission, and other were about the development of the community itself in the UAE. So I wanted just to put a slide in here about the engagement programs that we have. So we have set a wide range of engagement programs targeting multiple targeted audience within the UAE. We focused on students, we focused on professors and researchers, even retired teachers, and providing even other platforms for public to exchange knowledge, to develop scientific capabilities, and to provide opportunities for each and eager to be part of the Emirates Mars mission. So I will not go over any of them in detail, but if you have any question, I would be happily answering them. So this is where we reach the end of my presentation. I'm very honored, honestly, to be part of this mission from the beginning and to see how transformative this mission had been, not only for us as a mission team, but all for the UAE as a whole. And it was such an honor, to celebrate the success with the whole country and the whole international community, which were very excited for the launch of the mission. And I just want to end it in here that I hope that this mission has inspired everyone. And because to me, it's a special message. It sends to the youth that we have within the country, within the Arab regions and all. If we as a small nation can put such a huge goal in front of us and attain it and be able to succeed in it, everyone can successfully achieve their dreams whenever they put their goals and whenever they put their goals into action. So step by step, we reached in here, and we can't wait for the 7 months to be over in order to see the first image that we will get out from the hopeful for Mars. Thank you very much.
Thank you.
Thank you, Hessa. I'm applauding on behalf of all the audience. Thanks for the great talk and congratulations once again for the successful launch. To save time, we are not allotting additional time for Q&A. All the questions will be through the Q&A feature. And Hessa, it would be great if you can just type them out. We have 8 questions so far. So in these difficult times, as you know, we need hope, but we also need perseverance. And that is the name of NASA's mission. It is the most complex instrument to land on the surface of Mars. It is scheduled to launch on July 30th from Florida. And to talk about it, we have Dr. José Antonio Rodríguez-Manfredi from Spain's National Lab for Space Research. He's at the Astrobiology Center there. He's the principal investigator of the MEDA instrument on board the rover, which is going to take very critical measurements there. So Jose, thank you for joining us, and please go ahead.
Thank you, Dimitra. Can you see my screen? Can you see the main screen with the presentation?
Yep. We can.
Yep. Okay, so once again, thank you so much for your kind invitation. This is great, and of course, I would like to start congratulating you all, congratulating the entire country for the success of this recent launch, and wishing you all the best for the success in the years to come. So the space program and the exploration of Mars, as you've been undertaken, is very meritorious, as you were saying. So congratulations and go up. So of course, I would like to thank NYUAD and UAE Space Agency for this invitation. And this is really great that this talk comes after, at this point, after my colleague's great presentation, because in some cases, we're gonna be, covering different understandings of the same approach, and that is probably that's important. So this is not new. 2020 is going to be a very special and unique year in the exploration of Mars. Many different agencies are taking an active participation in that exploration, and I'm pretty sure that that will bring up good collaborations and synergistic approaches international at the exploration of Mars. From now on, given the complexity of the mission, will require international collaboration, and this is the way, probably the only way we may find a path to finally fulfill that exploration in detail. What you can see in the screen is NASA's strategy. NASA's strategy is, of course, as we said before, giving floor not only to the science, exploration, and technology, the exploration technology, but also to the industry. We said that before. This is really important. That the industry in the country takes how to know this. That will create emergency richness in the country, not only about knowledge, and this is also important for the different countries. In this strategy we're now facing, the main goal might be the seek for sign of life, the search for life, as we really understand now. But of course, there are some steps in between, and of course, being ready for the human exploration at the end. This is going to be crucial. If we finally attempt to get out of our country, we have to develop technology. We have to increase our knowledge. We have to understand this enterprise from different perspectives. And this mission, Mars 2020, is intended to be a singular step in the process. You can see on the screen how this strategies on the Martian exploration started with following the water, as we understand that we should not fall into the misunderstanding of searching the kind of life we have on Earth. But anyway, we have to base our strategy in the knowledge we have. Of course, we have to open our mind and then be ready for other, life forms. In this particular case, following the water has been actually the first step in that process. Exploring the habitability is a needed step, linking the water, the presence of water, with the other key elements we may need to finally find life. Or, yeah, find life, not meaning present life. We should also think on extant and extinct life. So in that context, we will be following a well-known path that will eventually provide some evidence of the presence of life beyond our country. In that case, if we try to solve this main question, the search for life, what should we be looking for? If we rely on what we know from Earth, of course, we may find fossils like the ones you can see on the screen, but those fossils are less than 650 million years old. If we understand the evolution of the Martian planet, of Mars, we cannot expect to find those kind of fossils because the climatic change in the country happened well before that, as we saw in that previous slide. So if we really want to look for some kind of evidence of life, thinking on the kind of life, in the parallelism with the Earth life, we should start looking for those kind of microbial biosignatures. Those biosignatures we found on Earth happened 3.6 billion years ago, for example, that order of magnitude. So that is putting us on the clue of the kind of, environment, of the kind of features we should look for on Mars. And in that context, relay that with the paleoclimate the planet Mars used to have on those days. So that's why, and I'm going to my particular, say, area of expertise, that is the Martian atmosphere. That is why the Martian environment is essential. Understanding the Martian environment is essential, as we also saw in the previous talk. So this, the current environment will lead us to study and model and go back in time to finally understand how the planet and its climate dynamics evolved from those days up to the current situation now. But not only that, if we want to go to the surface, and especially if we want to go to the surface with a human tripulation, with a human crew, we should have a quite good understanding of the Martian environment, because, well, this is not just a few hundred kilos or a ton that is landing. We're talking about human beings, and so the risk is, tremendous. So we have to make ourselves ready to land on Mars with a huge spacecraft with human beings on it. And that is why one of the most important topics in all agencies' roadmaps are the really understanding of this atmosphere and atmospheric conditions, not only from this the science's perspective, but also in terms of that engineering aspect of the missions that will give the confidence to land on Mars with those huge spacecrafts we're developing. Oh, I'm sorry. I was talking about all this and didn't. I'm sorry. I thought it was the other slide. So that is what I was describing. So that was really clear from the very beginning. NASA has that in mind from the 1975 for the Viking missions, you can see here, and in which we had a small set of sensors to at least some magnitudes characterize that environment, local environment. So you can see how all this is, in some sense, complementary with hope. We're going to be understanding and we're going to be measuring all those conditions, atmospheric conditions, weather and climate, in some sense, from orbit. And with these missions, we're providing the complementary understanding of that. Of course, they will correlate, but these two perspectives, these 2 points of view are really essential to coordinate and engage. Almost all missions sent to the surface of Mars have their own meteorological package. I don't want to go into the details. This is Mars Pathfinder, and you can see how, you know, there's plots, there's sensors for logging all those magnitudes. This information has been essential up to a few decades to understand that and being able to land on Mars. So Viking data has been used until very recently to understand that and, you know, design MER, for example, MER missions. But there was a really before and after in the Martian exploration with Curiosity, with Mars Science Laboratory mission, in which we had a chance to participate with the REMS instrument. The environmental station, that's even beyond a weather station, the way we understand that. This is becoming more crucial if we understand the evolution of the Martian exploration on the surface. Looking at this nice picture, this is the family portrait. So on the right, you have the Pathfinder rover that was about 10 kilos. And in a decade, or well, couple decades, less than couple decades, we've been going from those 10.5 kilos to almost 900. And in the case of Perseverance, we're now talking about 1 ton, I think it is, don't know exactly the number, but it is about 1,050 or 80 kilos. So this is huge. And so the knowledge of the atmospheric dynamic is crucial. This is not trivial. Landing on Mars is not trivial at all because of the communications delay. We have to rely on the knowledge we have to pre-design a landing strategy, not only the hardware, but also all the processes to land automatically on Mars, independently on the environmental conditions that may be happening at that particular time. So that knowledge, again, from orbit, together with information, the knowledge and understanding we can and we should provide from the ground, from the surface, that knowledge is essential. With REMS on MSL, the instrument we developed for that mission, we started contributing to that. Signing an instrument to measure the winds, the local winds, horizontal and vertical winds, the temperature profiles, the albedo, and the ground temperature and the evolution of that, the pressure, humidity, relative humidity, and the radiation. The radiation, as you can understand, is crucial on the surface. I mean, it's crucial thinking on the environment, the astronauts or the cosmonauts or the taikonauts, independently on the country, will need to survive on. So that knowledge will be putting another stone in the, in the path to finally being able to land humans on Mars. So in that context, from 2012, when we landed on Mars, RAMS and Curiosity has been providing a lot of essential information that is, providing that knowledge about the mesoscale, not a general understanding of the global, not only about providing that context in the general circulation, but also in the mesoscale level that is also needed, thinking on that potential landing. Of course, the environment in general, we have a lot of implications to understand how the geology has been modeled along the years, along the million years. Essentially, the geology is affected, and even the mineralogy is affected by the radiation that comes to the surface. So understanding that is essential in terms of providing a context to understand what we find on Mars. And as a summary of all this, Curiosity was able to provide evidence on that ancient habitable environment. So we know there was an aqueous environment with a relatively neutral pH because of the minerals we observed in there, with a relatively low salinity. And well, essentially that environment, I'm talking about 3.6, 3.8 billion years ago, was a habitable environment. Able cannot for sure ensure that there was life on those days, but environment was convenient for life, say that way. There was a potentially habitable environment. We also, with the instruments, we also provided a detailed characterization of the atmospheric species. This is no, but we were able, the mission was able to quantify very precisely the abundance of those species, CO2, mainly CO2, what is an important step in the design of some technologies, as we will see in a minute, to extract the oxygen out of that atmosphere, the Martian atmosphere. This is one of the main objectives Perseverance will have. And this is relying on, of course, the knowledge we've been gathering all this from all the sensors and instrumentation from the previous missions. 2% argon and almost 2 of nitrogen. And within this context, I think this is important to step just a little on the capabilities Perseverance will have. So what you see, we'll be having a new generation instrumentation that in most of the cases, or well, in all the cases, have been developed also from 2014, taking advantage of the knowledge and the expertise we've been gathering from the missions, from the previous missions. In our particular case, Mheiri is the Spanish contribution to the mission. Will follow these steps. We started with RAMS, as we saw a minute ago, and also twins on InSight. Didn't put it in here because InSight is, say, another nature in terms of the goal is not in line with understanding the habitability environment, but getting some deepest knowledge about the interior of the planet. But in any case, the instrumentation we contributed to this mission also is, of course, providing important data to correlate with RAMS in MSL and Curiosity, and also with Mheiri. In that sense, we can say we'll be having pseudo environmental network. So you have to understand, and this is important, a single station on the surface of a planet, Mars, or even here, on Earth is not enough to provide a global understanding of the weather and the environmental conditions in the planet. In case of the weather stations here on Earth, we have millions of them. And with all that information together and models, we can able to understand, in some sense, how the climate and the weather, the dynamics in general, behaves on Earth. In case of Mars, we just have, with lucky, we'll be having 3 in some months. This is not enough. You have to understand that this is not enough, but this is the first step. With the 3 of them, together with the models we have, with the environmental and atmospheric models we have, we can use those data as a ground truth and validation data sets to finally tune the models and finally have a better and an accurate model of the entire planet. In that case, that will provide another important perspective of the Martian environment. Perseverance has, at some point, similar science objectives to the ones MSL and Curiosity have. It will explore and characterize the geology with the instrument we'll see in a minute, and of course keep investigating the habitability potential of the planet, in this case on another landing site. But Perseverance has 2 important new objectives. One of them is the sample encaching. So taking advantage of the mobility of the rover, we expect to cover about 30, 40 kilometers. It depends on, the different circumstances, but on those, Perseverance will be able to sample and cache samples, rocks that will put in some vessels, will store in some vessels, and after the prime mission, the rover will deliver those vessels in a place for a future mission to come and catch and return to Earth. So in that case, Perseverance is going to be the first step in the plan forward to bring samples back to Earth. This is crucial. The technology that mainly JPL and partners have been working on over these years been really crucial, because those vessels with the sample should remain unaffected, unaltered, hermetic for years and decades, maybe, been able to survive to the Martian surface environment, radiation, and temperature ranges and so on, and being ready to for that Mars sample return mission in the future that will bring them back. So this is crucial and has been imposing quite important requirements on not only on the science, but also on the development of that technology. And of course, and not as important, we have to be ready. We're going to be working on that human exploration in some time, in some years, in some
Hi, Jose, sorry to interrupt you. We have about 3 more minutes.
Yeah, yes, I'm gonna finish in that time, yes. So, so the technology Perseverance will have are in some sense an evolution of some of the instruments MSL had, but in this case, these have been really improved. So having new generation cameras for driving and improving the navigation to finally fulfill that coverage I was saying. So it will have some lasers to analyze the rocks, remotely analyze the rocks, and some instruments on the turret at the end of the arm to analyze the rocks. in contact with the rocks. I mean, the proximity rocks. Perseverance is also having an instrument, carries an instrument, RAINFAX, that will provide, this is a radar that will be used to go inside the planet, trying to look for the features, the geologic features under the surface. I already mentioned before about META. META is the evolution of the RAMS and the TWINS instrument. And the main goals are, as you can see here, not only to understand, well, to log and then understand the near surface environment, but also to characterize the dust on the surface. Dust becomes crucial thinking on the potential human exploration because of the, well, dust is the main driver on the atmosphere, controlling the thermal profile, the radiation coming to the surface, but also because that may stop the filters some instruments will have. So understanding and having a good understanding on how that dust is and how the dust cycle behaves together with the winds and the humidity will provide an important milestone for that. I'm showing here some pictures of the new technologies we've been developing for META. This is an essential part of the development. META will also have a camera pointing to the sky to also study the water clouds on Mars. And as you know, we're now in Florida, ready for launch in 10 days, almost 10 days. An important instrumentation, this is a demonstrator. Perseverance will have its MOXIE, the technology to finally get the oxygen out of the CO2 the atmosphere has. And I'm not going to stop in this, but this is the vessel, the Perseverance rover has. And I'm going to stop here just mentioning about the new technology NASA wants to test, the Ingenuity drone, the helicopter that will provide a different perspective in the exploration of Mars. This is just a demonstrator, but in the future, I guess, technology, the exploration technology will rely on this kind of elements instead of the rover that have a limited, coverage. And my last one is about a brief comment about the landing site. It is going to land in Jezero crater. That is this is a delta, a river delta that provide good habitability features and may help us understand the planet, the Martian habitability. Yeah, that's all. That is my this is my last slide. Thank you, Dimitris.
Thank you, Jose. Thanks for the great talk, and we are all eagerly waiting for the mission to launch successfully, land, and send us data. We are preparing our numerical models to get ready for the data. Yeah, so thanks a lot, and please, people are asking questions, so please type them out using the Q&A feature. Let us move on. So let us go to the current missions already orbiting Mars. And for that, we have Professor Anil Bhardwaj. He's the director of the Physical Research Lab, which is India's National Lab for Space Research. He has been involved with several space missions. He is the principal investigator of the MENCA experiment, which is on board the Mars Orbiter mission. So Anil, welcome, and get started. You're muted. Your microphone is muted. It should be on the, yeah.
Okay,
yeah.
so can you hear me now?
Yep,
Yes,
yep.
we can, yeah.
Okay. Is the slides visible?
Yep.
Great. So very good afternoon from India. Good morning, good evening, good night, all over the world, wherever you are. First of all, let me heartily congratulate the EMM, that is the Emirates Mars mission, the HOPE team for the wonderful launch they had 2 days back. And I wish good luck to them for the journey to Mars. We all hope that hope will keep our hope and will also create new hopes. Also, good luck to and best wishes to NASA's Mars Perseverance mission. It is going to be launched soon. So it is going to be a very exciting time around Mars when so many spacecrafts will be working together and complementing the science coming out from each of these wonderful missions. I was told that this talk would be for a quite wide audience. And since now HOPE is just launched and it will pass through many mission phases before reaching Mars. So I thought I will bring you some of those challenges and excitement about the mission of Indian Mars Orbiter mission, which we call as MOM, and also talk about the spacecraft, the launch vehicle, and then of course the instruments and the science which is coming out from this mission. As you see here, we call this mission as the Mars Orbiter mission or the MOM, M-O-M, but it is also called famously as Mangalyaan. And the word Mangal stands for Mars and the Yaan stands for the spacecraft. And that is how the word Mangalyaan means Martian spacecraft. So we have this Indian MOM. MOM, we all know, stands now for mother. A lot of people call their mother as mom. So we have already sent the Indian MOM to Mars. And on the bottom, you are seeing here the three photographs at the bottom. One is the rocket, the launch vehicle. On the right, on the left side, you see the spacecraft. And in the center, you are seeing a big dish or antenna. And all these three elements has to work together to have a successful mission. Now, when you talk about this Indian Mars mission or the MOM mission, we had the launch on 5th of November of year 2013. And we reached the Mars or got inserted into the Mars on September 24th, 2014, after traveling for almost 10 months. And we got inserted into an orbit of about 400 by 80,000 kilometers, carrying 5 experiments on board. So I will be talking about all these aspects subsequently. But we had a planned lifetime of about 6 months, but now we have already spent about close to 6 years, and probably in next coming September 24th, we'll be completing 6 years in orbit around Mars. So this itself is a great achievement. But when we talk about planning this mission, we had scientific objectives in terms of what science we have to do, but more importantly, we also had a huge technological objectives in mind, because we are planning to have a mission which will be truly interplanetary in nature. So you have to talk about designing, planning, managing, operating this mission, going from Earth to Mars, taking 10 months, then getting captured. So you need to have a lot of technological advancement with respect to deep space communication, navigation and management, and a lot of autonomy features has to be built into this kind of missions because of the large travel time delays of the light. So when we had this mission, there were 3 main phases of this mission. One is that after launch, we went into an orbit around Earth, which you see over here. I don't know whether you can see my cursor on the screen, but which is with 1 given over there. And then on December 1st, we actually departed from Earth for almost like 10-month journey to reach Mars on 24th of September. So I'll be sharing some of the excitement of this mission profiling, how did we go about it. But after insertion into an orbit, we had a visitor called Comet Siding Spring, which was visiting Mars. luckily. But we had to be very careful about that because this was quite challenging, and we were worried that whether we will get bombarded by this long tail of the comet Sidus thing. So the orbit was actually perturbed within a few weeks of arriving on Mars, so that we are on the other side of the Mars and be safe for mission to continue. So this was the first challenge which came up, which was successfully overcome. Talking about the MOM spacecraft, it's a spacecraft of about 1350 kgs in mass, which is, I think, something similar to what the HOPE mission is. But we had to carry a large amount of propellant, and almost like 60% of the mass of the spacecraft was propellant, because we need that for escaping the Earth, going around the Earth and then escaping, and then getting inserted into an orbit around Mars, and then, of course, for survival. We had a big solar panel, which you see over here in the blue, and the big dish, which is about 2.2 meter, which is the high gain antenna, which is currently being used for communicating with the spacecraft. One of the challenges which came immediately when we were planning about this mission was that the two major events, the fourth stage separation of the launch vehicle, because PSLV is a 4-stage rocket, and of course the injection of the spacecraft from the launch vehicle, was happening deep down southern Pacific Ocean, and there's no land there. So one of the challenge was, how do we get the data of these two major events? So we overcome that by sending two shipborne terminals, Nalanda and Yamuna from India, and they were all stationed in the South Pacific to capture these two events, and which provide us the data that the orbit in which the spacecraft is put in is perfectly valid. On the ground, of course, we use the Indian Deep Space Network, which is the 2-meter antenna, but on the spacecraft, as I was just mentioning, we have a huge antenna, which is a 2.2 meter antenna, which is now communicating with the ground and providing us all the health parameters as well as data from the spacecraft. Another feature which we have to overcome when we talk about this long duration missions or long distance missions is that there's a large time delays. And for that, you need to be ready to have a lot of autonomies built into the spacecraft, which is essentially required for interruptions during eclipses and during whiteout and blackouts, which is essentially a time when the spacecraft, the Mars, the Earth, and the Sun are aligned either on the one side or on the opposite side. And for that, you have to build in a lot of autonomy features, which was incorporated into this kind of missions. And that was also useful during the Mars orbit insertion, as I will be talking to you later. So this is how the spacecraft is getting ready in the clean room in Bangalore, in our UAE Space Center. So you can see several subsystems getting assembled. This is about 1.5 meter cuboid structure. And you have this big tank, which is covered with this orange, with this pink color, which is required for the large amount of propellant which was carried by the spacecraft. And after all this is assembled, it goes under a huge space simulation chamber for testing the whole subsystems of the spacecraft to see its performance in space. And subsequent to that, we also test a lot of other features, including the solar panels deployment, the solar cells, and things like that, because this is essentially required for power generation, which is an essential aspect of the mission. And you need power in the spacecraft to run all the instruments as well as all other subsystems. So this is the map of the India, where you see here the red big circle in the southern part of India, where the assembly of the whole spacecraft takes place. And then it is sent to the spaceport of India, the Sriharikota, which you are seeing here in the green color, the big green circle, where the launch actually takes place. And you can also see a lot of dots all over India, which are basically the various centers of Department of Space and Indian Space Research Organization, where we do a lot of activities with respect to spacecraft development, the instrument development, the launch vehicle development, and the science aspects. So as it reaches the spaceport in Sriharikota, it is assembled on the top of the launch vehicle. Now you can see here the 4-stage rocket, The MOM spacecraft is sitting in the top. You can see here covered with this golden sheet, which is basically the MLI or multi-layer insulation. And on the side, you're seeing the two heat shields, which will engulf it like this. And then you are almost ready for the launch, except the umbilical cord, which you see here attached to the launch. Rest all is complete. And this whole assembly of the rocket essentially takes place in this building, which you see here next to the launch pad. So you can see here the 4-stage rocket, the Polar Satellite Launch Vehicle of India, which was assembled in this big building, which is seen here on the right side. And after the assembly, this big building actually starts moving back. So there's a big rail on the bottom on which this assembly building moves back almost like 1.5 to 2 kilometers away, and the launch takes place. And on the back, in the background, you are seeing also the second launch pad of India on the same spaceport. So we had the launch on 5th of November at 14:38 Indian Standard Time. And you can see the ignition taking place. And now you can see also another view where you can see the assembly building moved far back and the launch is actually taking place. And we had a fantastic launch. And after the launch, we went into an orbit, which is shown over here, which is something like 23,500 kilometers by 250 kilometers. And this was essentially required that we need to jack up the velocity of the spacecraft so that we can escape the Mother Earth. And this was all done in a very optimal way because we wanted to utilize as much less fuel as possible. So we used to have the firing of the engine of the spacecraft in the middle of the night whenever the spacecraft comes very close to the Earth, which is called the periapsis, and increase the velocity so that it becomes highly elliptical. And this continued for almost like 25 days when we had the last firing happening on the 1st of December in the middle of night, which you call as a trans-Mars insertion. And during this time, for about 25 days, we were also making sure that all the experiments on board are working. So this is one of the pictures which was taken around that time, where we see the image for the Earth taken from the Mars color camera. And on the 1st of December, when we had the last burn, which was one of the longest burn of the engine on the spacecraft for 22 minutes, we actually achieved a velocity greater than 11.2, which is escape velocity. And we started moving on to an orbit which is escaping the Mother Earth towards the Mars. Now talking about the spacecraft itself, you are seeing here different views of the spacecraft in the stout conditions, as well as sitting inside the heat shield or the equipment bay of the launch vehicle. But in the exploded views of how the spacecraft was made, you can see here in the completely open conditions where you see the various subsystems of the spacecraft as well as the payloads or the experiments. We had 5 experiments on board with the total mass of about 13 kgs. We had a huge, what you call, constraint in terms of the mass of the experiments because of the large requirement of the propellant to be carried. But we could accommodate 5 experiments on board, and they were Mars color camera, methane sensor for Mars, and thermal infrared imaging spectrometers. We had a laminar alpha photometers, as well as the Mars exospheric neutral combustion laser, the MANCA experiment. The first one is basically a RGB camera, which operates in the visible band. The second one is a methane sensor for Mars operating around 1.65 micron, essentially looking at the features of methane in the Martian atmosphere, but also it gives you also information about the albedos. And the thermal imaging, thermal infrared imaging spectrometer works in 7 to 13 micron. And that is the region where it will provide information about the surface temperature. And then we have a Lyman alpha photometer, which works in the H Lyman alpha of 1216 Armstrong. And then we have the Mars exospheric neutral combustion laser, the MANCA experiment, of which I was the PI. I am the PI, in fact, which is operating as a quadrupole mass spectrometer, working in 1 to 300 AMU mass range with 1 AMU resolution. These experiments are sitting and accommodated at different places on the spacecraft, which you see over here. The imaging payloads are all sitting on the one side of the spacecraft, the MCC, MSM, and TACE, as well as the lab. And they're all looking in the one direction because they are interested to look at the Mars. But the MENCA experiment is basically an in situ measurements of the neutrals present in the atmosphere and exosphere of Mars. And that is pointing upwards along the plus roll axis, and that is the axis on which you have the velocity vector also. So after insertion and going towards the Mars, we also had a plan to do mid-course corrections, because you need to know how the spacecraft is functioning and its trajectory and the velocities so that it reaches the Mars at the right time when the Mars is there. And we plan to have 4 mid-course corrections, which is mentioned below here, but we only required 3 of them because of the very perfect escape which we got from for the spacecraft on 1st of December. During the Mars orbit insertion, we also use not only our deep space network, but also the network of NASA, the ground support system of Goldstone, Madrid, and Canberra's, because this is all international cooperation and collaboration which happens. And NASA provided us support for the Mars orbit insertion. And this is just before, a day before the Mars orbit insertion. So this, you can see here, people from different stations sending best wishes. This is Madrid, this is Goldstone, Canberra's, and of course from JPL. And as is the tradition in US, that they also send good lucks as well as peanuts. So we also got a lot of peanuts along with the best wishes. So during the Mars orbit insertion, it was a very exciting event. We had to get inserted into Mars from the back side of the Mars. It is something like as you come along this line, which is shown over here in blue, you reorient the spacecraft and fire in the same direction which you're moving, because now you are reducing the velocity of the spacecraft to get inserted into orbit around Mars. But if you see the location of the sun and the Earth, they are on the other side. That means you will not have sunlight falling on the spacecraft, so everything will be on batteries. And then since it is also on the other side of the Earth, you will also have a communication blackout. And that is what was happening during our Mars orbit insertion. Within a few minutes of the firing of the engine, we were in the blackout period as well as communication. We are in the shadow as well as communication blackout. And that continued on for almost like 20 minutes. So this is where I was telling that spacecraft has to have a lot of autonomy features built in and to function of its own when you cannot communicate with the spacecraft. We had the signal blackout happening almost like 22 minutes before the orbit insertion. And at 8 a.m. in the morning on 24th, we got the news that the MOM has successfully entered the Martian mission. This is one of the pictures which we got from the mission after insertion. And that made actually India the first country in the world to have the successful insertion of an orbiter around the Mars in the first attempt. Soon after insertion, we started operating various instruments, but of course, we were also happy that the MAVEN mission has arrived there 2 days before. So this is actually a cartoon depicting the MAVEN and the Mangalyaan, India and US celebrating jointly around the Mars. And one of my colleagues from US sent me this photograph on the evening of 24th, sending that the MOM has become so famous that it has come on the Coke diet. And so that was also very exciting, because this is the type of excitement one gets. And I hope the whole team, which the engineer Fahad was talking about, the huge excitement they got during the launch, but much more excitement we are going to get once the Hope actually enter into an orbit around Mars and really starts doing the science. About a month later, of course, the Google had a doodle celebration on 24th of October of Mangalyaan around Mars. So these were all very exciting moments for all of us. Now coming to what kind of science is coming out from this kind of missions, because it's in a highly elliptical orbit around Mars with a very low inclination, we are able to see the whole disk of the Mars. And now for almost like 6 years, that means 3 Martian years, we have this kind of whole disk images of the Mars. And we can see how the morphology, or basically how the patterns on the surface of Mars are changing. You can see over here, now this is a different picture at different solar longitude, which shows about the north and south poles freezing because it is at the apoapsis. We also have the Mars color camera, which I just talked about, and which is an RGB. And this provides information about the various, what you call the dust and the clouds, which can be taken out, and one can study them separately, as well as completely make a color picture of that. So you are seeing here one of those images which you can study in the red, green, blue, but you can combine together to make the whole color image. And this is what is being now used by scientists to understand the changes in the atmosphere as well as the surface of Mars. This is one of the pictures where you can actually see in the middle is a huge cloud over here, and you can see the shadow of that falling onto the surface.
Hi, Anil, giving you the 5-minute warning.
Sorry?
Giving you the 5-minute warning.
Okay, fine. So this is also Phobos passing in front of the Mars. We also saw a lot of information about the Valles Marineris. You can see here that it is all filled with clouds and dust in some part of its, some time of its seasons, but one can very clearly see in the MCC images the clear-cut Valles Marineris. Olympus Mons has been studied extensively well by various experiments on board, particularly looking at the MCC images of the North Polar Cap. You see here, it changes as a function of time. We are also seeing a lot of clouds of ice getting formed, and they are basically coming on one side, which is the wind blowing side of this mountains. And we are able to now understand how this cloud formation happens and which part of the season this formation of clouds happen on the river side. We also see very interesting features of very high altitude scattering layers, which could be somewhere around 100 to 200 kilometers above the surface of the Mars and completely detached. But they are seen on very rarely. We are seeing some of them here in 2014, but we could not see much later on. And we are still trying to correlate this information with respect to what was happening around that time. MSM was able to provide us albedo at 1.65 microns of the whole disk, as seen over here, which is going to be very useful information at this wavelengths. And when you talk about the Menka experiment on board, which is basically called a Westermann spectrometer, this has provided us information about the exosphere of Mars, looking at the evening time exosphere. And if you look at this picture, which is basically showing you the orbit of the Mars around, orbit of the MOM around Mars, and the yellow box shows the observation time, which is expanded in terms of the composition on the left side. One can see that as you move up into the atmosphere, you are moving from a CO2 dominant atmosphere to an oxygen dominant. But the question is at what altitude the oxygen actually takes over CO2. So this is what is shown over in this, where you see that the O takes over CO2 and an altitude of something like 250 or 260 kilometers to almost like 280 kilometers in the evening time atmosphere, which is very different than in the noon time, where the altitude of transition is somewhere around 220 to 230 kilometers. And this is very, very important parameter because that has implications for energetics and dynamics of the atmosphere, because the energy deposition is governed by which species dominates in the upper atmosphere and exosphere of Mars. One can use this information to derive the exospheric temperatures, which is shown over here for some of the observations, which suggest the exospheric temperatures to be somewhere around 260 to 280 Kelvin, which is quite similar to what MAVEN is also seeing. Another important result which came out from this observation is the superthermal argon in the exosphere of Mars, which is essentially meaning that we are seeing argon which is slightly higher in temperatures, or you can say that two different temperature profiles of argon, which is shown over here on the right side. where one of them is having temperatures of about 150 Kelvin higher than that in the normal circumstances. And the implication of that is that once this higher energy argon or higher temperature argon is present in the exosphere of the Mars, then there'll be likely chances of it escaping, because the exosphere is the region where you don't have collisions. And therefore, this will have implications for the escape of the Martian atmospheres. So we have a lot of information now coming out from the MOM-Menka experiment, which talks about that we need to look at the escape rates of Mars, particularly when you have hot argon or hot CO2 present in the exosphere of Mars. Many of this information has come on the cover pages of various journals like National Geographic, which is shown over here. And Government of India, understanding the technological awareness which has come out from this mission, and to celebrate that, Government of India has put the MOM mission on the back of the 2,000 rupees currency note, which is over here, which basically talks about the technological advancements which has come out from this kind of missions. And I hope that UAE too will be having some kind of new way of celebrating after the HOPE mission gets inserted into an orbit. We also look at the two natural satellite of Mars, the Phobos and Deimos, using this MOM mission. And you're seeing here two of them, Phobos on the left side and Deimos on the right. You can even see Deimos on this picture, which was basically target to look at how the Deimos looks like. And this was only achievable because of the highly elliptical orbit. We could target this satellite and to look at different phase angles and come out with much more information. But very recently, we have got this same image of Phobos on 1st of July this year. This was also taken from different phase angles and then combined together to make the images. And that shows that the spacecraft is working very fine and healthy. And of course, it is now more than 6 years, or in fact 7 years since the launch. So aging is taking place on the spacecraft with respect to various subsystems, but still it looks to be quite healthy. And we hope that we will have some more time making observations of the Mars using the MOM spacecraft. So with this, I would like to thank you all for providing me this opportunity to talk on this mini virtual symposium on Mars 2020 and beyond. And I hope that this is going to be a very exciting time ahead for all of us, celebrating various missions, arrival at Mars, and then looking at the exciting time with respect to the science. So thank you all for listening patiently. And I hope you all take care of yourself and stay safe. Thank you.
Yeah, thank you.
Thank you, Professor Bhardwaj. Thanks a lot. And as you mentioned that MOM and MAVEN reached the Martian orbit around the same time. And so that is why we have kept the two talks together, MOM and MAVEN. And MAVEN in many ways is a precursor to the Emirates Mars mission. To talk about it, we have Professor Bruce Jakosky from University of Colorado, Boulder. He's the principal investigator of the MAVEN mission. He's also a member of the EMM Science team. And thank you, Bruce, for joining us so early this morning for you.
Good morning. Thank you. Can you hear me?
Yeah.
And can you see my slides now?
Yep.
Thank you. It's a real pleasure to be here today, especially following the wonderful launch a couple of days ago now from for the HOPE mission. What I want to do is talk about, talk about the history of the Mars climate and some of the results that came out of the MAVEN mission. This is particularly relevant here because in many ways the HOPE mission builds not only on everything else we've learned about Mars from all the other spacecraft, but particularly it builds on the results from the MAVEN mission. So what I'm going to do is try to set the stage. And of course, I have to start off with this, that HOPE is on its way to Mars. This is a much more fun seminar than had the launch not gone successfully. I want to point out that where I am, launch occurred on July 19th, but in the United Arab Emirates and at the launch site, it was July 20th. And July 20th is a very auspicious day. That's the anniversary of the Apollo 11 first human landing on the moon. It's also the anniversary of the Viking 1 first landing on Mars. So now there is a third event to celebrate that day, and that is the launch of the HOPE probe. I'm hoping that July 20th will become International Space Day, and we can celebrate it for a long time to come. What I want to do is talk about the science that has come out of MAVEN. Anil Bhardwaj just gave a very nice presentation that included some of the discussion of how you get there. And MAVEN was very similar in terms of development, testing, launch. So let me focus on the science. When we look at Mars today, it's a very cold and dry planet. Temperatures 50 degrees C below the melting point of ice, the freezing point of water. Thin atmosphere, very, very little water in the atmosphere, and no possibility for liquid water to exist at the surface. The upper left image here is the surface of Mars as photographed from the Viking 1 lander some 40 plus years ago. However, we think that this has not always been the case, that early in Mars history, it was a much wetter, warmer place. We see evidence for that, for example, in the upper right image, which shows river channels. These occur on the ancient surfaces and suggest that Mars at that time was warm enough to allow liquid water to flow over the surface. The bottom two images are Jezero crater, where Perseverance rover will land. On the bottom right, we see the whole crater. It was a lake at one time, an impact crater filled with water. In the lower left, you can see some of the deposits laid by water flowing into the crater. To have liquid water stable, to have liquid water flowing requires a very different climate from what we see today. The question that we've been looking at is, where did the CO2 go from that early thicker atmosphere? Where did the water go? And the volatiles can either go down into the crust. We see evidence for that in this case, one of the Martian meteorites that showed deposits that require liquid water. Or volatiles, gas in the atmosphere, can go up to the top of the atmosphere and be lost to space. We see here escaping ions detected from the Mars Express spacecraft. These tell us that the gas from the atmosphere went both up and down, but MAVEN was designed to explore how much gas has been lost to space. We had instruments that looked at the composition of the upper atmosphere, the solar energetic input into the upper atmosphere, and the material, the atoms and molecules that were being lost from the upper atmosphere. The lower right image, that's the reason I have this chart in here, shows the orbit of MAVEN. And with that elliptical orbit, we pass through the entire upper atmosphere, every orbit. So from the top of the orbit, the highest altitude, we can image the whole planet and see what's happening globally. From the bottom, we get very detailed observations of one place. And over the course of now 6 Earth years, as Anil said, almost 3 Mars years, we've been able to observe what's been happening. And I want to talk a little bit about what we've seen. The water and the CO2 are the main climate-related gases. And the first observations we had showed the atomic gases, the carbon, the oxygen, and the hydrogen broken apart from the CO2 in the water and producing this extended corona of atoms around Mars. Carbon on the left, oxygen in the middle, hydrogen on the right. In essence, we're seeing the atoms as they're on their way to escaping. So this is the first part of understanding the escape from the atmosphere. We were able to measure the ions being stripped away from the upper atmosphere by the solar wind. This image shows one entire Mars year of data assembled together. The sun is on the right. The solar wind accelerates the ions and removes them from the planet. The arrows here show the direction and the velocity that the ions are moving, and the colors represent the density of the gas. You can see gas being stripped away over the top of the planet and going down the tail away from the sun. We're able to add up all of these atoms and estimate the total loss rate today. In addition to ions, we were able to measure neutrals being lost. We were able to determine all of the inputs into calculating the photochemical loss of oxygen from Mars. The data are shown in the upper figure, and it looks like a random collection, but you have to remember that the orbit of Mars is precessing, and we're seeing a lot of different local times and local times of day and latitudes and longitudes. When we sort it by how far away the point is from the subsolar point, you get the image on the bottom, the graph on the bottom, and it shows clearly that on the day side, where the sun is shining, you get lots of escape, not a surprise since it's sunlight-driven processes. And if you look carefully at the colors, they are color-coded by how much ultraviolet light from the sun is hitting Mars, and you can see that that also exerts an influence. The key result here is that this photochemical loss is the greatest loss rate today. If you add up all of the loss from the atmosphere, we're seeing loss at a rate of a couple of kilograms of gas per second. That doesn't sound like much, but over long time scales, it can add up. And in particular, when you consider the fact that the sun was more energetic early in its history, the total amount of gas lost from the atmosphere is equivalent to about 1 or 2 times the amount of gas in the Earth's atmosphere. So loss to space is able to explain a significant loss of gas from the Martian atmosphere. But it's even worse than that, because there are solar storms that occur intermittently, and these have an effect. We saw one very significant storm in September of 2017, a couple of years ago. This is an image taken from the Earth of a storm like the one we observed. You can see the gas being ejected to the right of the sun here. The sun, of course, is blocked off. You can't see it because it would be too bright. But when that storm hits Mars, all of those energetic particles traveling at thousands of kilometers per second can damage the Mars atmosphere. And one example of that comes from the aurora. We've seen aurora over the planet, but in this image on the left, just before that storm hit Mars, you can't see an aurora. What you're seeing here is noise. You can't even see the limb of the planet on the left. Immediately after the storm hit Mars, you see the image on the right. The colors are at the same scale. Basically, Mars lit up like a light bulb. All of these energetic particles come in and stimulate the emission of light, which is what an aurora is. In addition, they can strip gas from the atmosphere. And what we saw was during this event, the amount of gas being removed from the atmosphere increased by about 10 times. These events were more significant early in the sun's history, early in Mars' history, and we think that this may have been a dominant process for removing gas from the atmosphere. So we've been talking so far about CO2 being removed from the atmosphere. What about CO2 being lost down into the crust? We know that, that volatiles can be lost down into the crust. We see carbonates. We see minerals like hematite shown in these nodules in the upper left that require liquid water to form. The liquid water is a very efficient agent for removing CO2 from the atmosphere. The image on the bottom right from the Curiosity rover shows deposits of sediment laid down in water. Again, the water allows for CO2 to be removed downward into the crust. We can map the CO2 bearing minerals from orbit. This isn't done for MAVEN, but we're looking at integrating all of the results together. We see carbon-bearing minerals at many locations. When we add it up, we can identify two types of deposits. Surface deposits, where large deposits are exposed at the surface. And the type example of that is Neely Fosse, where there's green dots near the Isidis crater toward the right up here. Those deposits contain the equivalent of about 12 millibars of CO2. That's 12 1,000ths of the amount of gas in the Earth's atmosphere. It's a very small amount of gas. We can also identify carbonates that are buried deep in the crust, and these are exposed by impacts, which bring them up to the surface, or by tectonic features. It's very difficult to quantify how much CO2 might be buried there because we only see it in isolated places. It could be a small amount, it could be a large amount. If we add up all of the sinks for CO2 on Mars, we can determine how much CO2 there might have been in the atmosphere. I've been talking about stripping to space, which removed 1 or 2 bars, 1,000 to 2,000 millibars. That is 1 or 2 times as much gas as is in the Earth's atmosphere. Impacts early in history can eject gas to space. That removed a significant amount. And if you look at the others, polar ice, clathrate, near surface carbon-bearing minerals, these probably don't contain a lot of gas. If you add it all up though, you get 1.5 to 3 bars maybe of CO2. What's important is this is enough CO2 that it would produce significant greenhouse warming early in Mars history and allow liquid water to be present. What about the liquid water? Where did it go? We can look at the hydrogen in this extended corona and see that it's escaping to space. We can quantify how much hydrogen is being lost by looking at different isotopes of the hydrogen in the water. This is a schematic diagram of a water molecule with an oxygen and 2 hydrogen atoms. Normal water has 2 hydrogen atoms. Heavy water has, in addition to the oxygen and 1 hydrogen, an atom of deuterium. Deuterium is just hydrogen that has an extra neutron, so it's twice as heavy, but it still makes the same water. When the water is broken apart by sunlight and the hydrogen wants to escape, the deuterium is much heavier than the hydrogen, so it escapes much less readily. As hydrogen escapes, the lighter stuff escapes preferentially, and the gas remaining behind becomes enriched in the heavier deuterium. We can use that ratio to tell us how much water has been lost, how much hydrogen has been lost. On Mars, the ratio of deuterium to hydrogen is about 6 times what it is on Earth, and that means that somewhere between 85 and 99% of the water has been lost to space. This is the equivalent of a global ocean as much as 500 meters deep that has been lost. So we're seeing where the water has gone, where the carbon dioxide has gone, and our results indicate that loss of the atmosphere to space has been a major process in the evolution of the atmosphere. And it's consistent with the idea that early Mars was much warmer and much wetter than it is today. So Mars went from being a warm, wet planet that maybe was conducive to the formation of life to being the cold, dry, desert-like planet that we see today. Is it possible to make Mars warm and wet again? In other words, can we terraform Mars, change the environment to be more conducive to having liquid water or more conducive to people working there? There are people who want to terraform the Mars environment in order to have colonies there, in order to live there. The best approach to terraforming Mars would be to add a greenhouse gas to the atmosphere. And if we want to use modern, present day technology, we have to think about CO2 as a greenhouse gas. We know that CO2 is a greenhouse gas, very effective one here on Earth. What can it do on Mars? Is there enough CO2 to allow us to do this? We can look at where the CO2 might come from. There's CO2 locked up in the polar caps. We can get CO2 out of the ground where it's attached molecule by molecule to the dirt grains. We might be able to heat up the CO2 bearing minerals and drive the CO2 out of that, or we can wait for continued volcanic outgassing to replenish the atmosphere. Can we add these all up? I've shown you this chart before. It's where all the CO2 went. I want to change it. I want to ask how much of the CO2 can be mobilized and put back into the atmosphere. So let's go through these. The first is impact ejection to space. It's gone. Once the CO2 is ejected to space, you can't get it back. What about the oxygen, the water, the CO2 that's been stripped to space by the solar wind? Again, if it's been removed, you can't get it back. There's polar ice, and we think it contains about 6 millibars CO2. That's about as thick as as much gas as is in the Mars atmosphere today. If we heat up the polar caps, we can get that back. So that's a win. There might be an ice structure called a clathrate that is a mixture of water and CO2. If we can heat that up in the polar regions, we can get no more than about 30 millibars back. That's as much as there might be. What about the near surface carbonates? These are carbon-bearing minerals. They can release their CO2 if you heat them up, but you have to heat them up to about 300 degrees C. That means you'd have to strip mine that part of the planet. I don't think that's feasible, so I'm putting that in the no column. The adsorbed gas that is bound up in the regolith, you can get out by heating it up relatively little. The problem is you heat it up, and when you stop heating it, it goes right back in. So I'm counting that in the no category. And the deep crustal carbonates, there might be a lot of gas there, but that's buried 3 to 5 kilometers down. And if you wanted to release it again, you'd have to strip mine the whole planet. So the bottom line is there really isn't a lot of CO2 that can be mobilized. Can Mars be terraformed? Well, the real question is, can be terraformed using today's technology? That is by getting the CO2 out of the crust and into the atmosphere. And I think the answer is no. However, we can ask a question, can we do it if we have different technology? As an example, we might be able to use the carbon and chlorine to create very high efficiency greenhouse gases, like chlorofluorocarbons that we've manufactured here on Earth. You can imagine doing that. There are gases that you can make that would be very effective, but that requires a serious manufacturing capability on Mars. And I'm going to put that as a question mark. It's far into the future. I'm looking forward to the opportunity to send people to Mars. And maybe after we send the first person successfully, we can think about long-term civilization or factories that would manufacture terraforming able greenhouse gases. This is my last chart, and I wanted to leave with the emphasis on what's coming next. We've seen the Perseverance rover that's coming next. The HOPE mission launched a couple of days ago. It is on its way to Mars, and it's going to provide the next step in our understanding of the Mars environment by studying the weather today and the history of gases through the history of the planet. We're going to get a much better understanding of how the atmosphere works, how the volatiles work, the gases, and where they went. And that's going to be important for understanding the habitability of Mars by microbes in the past or possibly in the subsurface today. And it's going to tell us about, if there is life, how it would have interacted with its planetary environment. So I will stop there. Thank you again for the opportunity to talk with you. This is a very exciting time, both for the UAE and for Mars exploration scientists globally. Thank you.
Thank you, Bruce. Wonderful talk.
Thank you, Bruce. That was a great talk. And yeah, thanks to the entire MAVEN team for providing such wealth of data to understand the Martian atmosphere, and future missions will build upon that work. I read, MAVEN papers almost on a daily basis, and so thanks a lot for that. So we are running a little late, and while the talks were going on, I was editing my talk and making it much shorter. So I'll be really quick, and I'll give a quick overview of Mars research we do at NYUAD. All right, can you see my slides? All right, thank you. So my name is Dimitra Atri. I'm a research scientist at the Center for Space Science at NYU Abu Dhabi. The center, the principal investigator is Professor Srinivasan, as you guys know. Our center, we have expertise in solar, stellar, and planetary physics. We have co-investigators with expertise in high performance computing, extrasolar planets, heliophysics, stellar physics. We have a number of postdoctoral researchers working in various fields, including the fields I mentioned and on machine learning. We have a graduate student, Shane Carberry-Morgan, who is working on atmospheric escape, and he will be using EMM data for his research. Aza is studying the impact of radiation on astronauts, which is going to be the future of UAE's space missions, I hope. In addition to this, we have several students who joined us recently, starting in July. We have many students starting in August. So we have a growing research program on Mars. We are already studying data from a number of missions and looking forward to data from HOPE and to be able to do research here in the UAE. We have a mix of both Emiratis and international students. So as I mentioned that we have expertise in both solar stellar physics and in planetary sciences. So my job is to combine the two, and I study how solar radiation impacts planets, especially Mars. So space weather include solar wind, flares, CMEs, energetic particles, basically energetic photons, extreme ultraviolet, and energetic charged particles, protons, electrons, and so on. And once they interact with the Martian atmosphere, we study their interactions in great detail. We have numerical models where we apply their physics. We study how it heats the atmosphere, excitation, ionization, all the electromagnetic processes and hadronic processes in case you have energetic protons. All these physical processes drive two things of interest for us. One is atmospheric escape, as we learned from all the previous speakers, why we study that, plus how it changes the chemistry of the Martian atmosphere. On the right, you can see this cartoon where it shows, a number of channels of escape, and it is a very complex problem. And we want to understand what type of radiation causes what channel of escape, and that is where we will dig deeper. And we are already learning a lot from existing missions, and EMM will add to that understanding. I am showing one EMM's instrument, EMUS. It is going to look at the thermosphere and exosphere of Mars, so 100 to 200 kilometers, beyond 200 kilometers. It is going to look at oxygen and hydrogen, and all these processes that I mentioned earlier affects their abundance. And so we are going to study how our numerical models compare with the data from this instrument and learn some new things about the Martian atmosphere. So the main questions overall that we are trying to answer is, how does solar activity impact Mars? How did Mars lose a majority of its atmosphere? It is of great importance to planetary science in general. And we also want to apply all these studies to other solar system planets. So I have worked with Venus, on Pluto, which is a dwarf planet, plus on extrasolar planets. We already have 4,000 extrasolar planets so far, and it would be really interesting to apply these sophisticated models and compare with those observations. in addition to this, we are also interested in the human exploration of Mars. The next step, a number of space agencies are working towards that, sending astronauts to the moon, to Mars. UAE already has an active astronaut program. So we have this software, which is called Geont4. It is developed at CERN. And it is used to study how high energy particles interact with matter. And we have used this to study how it impacts different body parts on astronauts. Now, the interesting thing is on the way to Mars, the estimated radiation dose compares to what radiation dose is used for cancer treatment. And so we already have medical data, and so we are comparing these astrophysical measurements with our radiobiology calculations with actual medical data, and it has implications for human spaceflight. And so we are leading a big international collaboration. Our manuscript is already more than 50 pages long, so we might have to cut it short a little bit. So finally, this is a very interesting question. Professor Jakosky also mentioned that there might be a possibility of life below the surface of Mars. And so I have a paper accepted in Scientific Reports coming out on July 28th. We are under embargo, so I cannot show you any results, but I'm showing you a picture. You can get an idea, so please keep an eye on this. We will announce it soon. So overall, we study the Martian atmosphere. We are interested in crewed missions to Mars, possibility of life on Mars. And how does the human exploration of Mars redefine sustainability? What can we do about, can be improved with the concept of sustainability on Earth with all these future missions to Mars? This is the overview. We have many people working on this, both international students and Emiratis, and we want to expand our research program. In addition to this, we have a space science webinar series. So our Center for Space Science, in collaboration with the UAE Space Agency, every Tuesday at 3 p.m. So if you're registered for this event, you're automatically registered for our webinar. We invite experts from planetary science, solar and stellar physics community to give talks. Finally, thanks to the UAE Space Agency and our center for making this event possible. Thank to all the speakers. I've been really excited for this event. Have been looking forward for a very long time. In particular, I want to thank Professor Srinivasan, Dr. Fatima from the Space Agency, and Tamara Withers from our center for coordinating and making this event possible. And we hope to have a much bigger event on Mars sometime in October, hopefully. So thank you. Thanks a lot.
Thank you, Dimitra, for this. And I want to say thank you to all the speakers and congratulate again the UAE Space Agency and the MBRSC for this extraordinary success. And congratulations to the whole citizenry of UAE. It's an exciting time for Mars, and we certainly hope to be able to be part of it. Thank you, ladies and gentlemen. Bye from my end.
Thank you, everyone.
Thank you all for this. I definitely learned a lot and appreciate having been invited. So look forward, inshallah, to the next one and hope to learn more. Thank you.
Thank you, Engineer Fahad.
Take care.
Thank you.
Thank you. Bye.
Thank you. Bye-bye.
Thank you, Professor Bhardwaj.